Hi guys, in this video I am going to explain about Hartely oscillator and find the frequency and beta value. Firstly, Hartly oscillator is an electronic oscillator circuit which produces sinusoidal output signal. First we will draw the circuit diagram. So this is the CE configuration. So this is CB, this R1 and R2. These two resistors are used for the biasing purpose. This is the base, collector, emitter. This is RE resistor, CE resistor, RC, and this is VCC, and this is CC coupling capacitor, and this is the output. This is L1, L2, C, and we're gonna give these two inductors to the ground. So coming to the derivation part, we're gonna consider this in a j omega domain. So Z1, Z2, Z3. So Z1 inductor, L1 inductor we're gonna represent in a j omega format. So Z1 is equals to j omega L1, Z2 equal to j omega L2, and Z3 we're gonna use a capacitor which we gonna write as 1 by j omega c, which is minus j by omega c. Now we gonna substitute these three terms in the general equation of LC oscillator, which is Z1 Z2 of 1 plus HFE plus Z1 Z3 plus HIE of 1 Z1 plus Z2 plus Z3 equals to 0. Now we should substitute these three terms in this equation. So Z1 equals to, which is j omega L1, Z2 into j omega L2 of 1 plus HFE plus j omega L1 into minus j by omega c plus HIE of 1 omega j omega L1 plus j omega L2 plus minus j omega c equals to 0. So we're gonna multiply these two, j into j minus, we're gonna get omega into omega, omega square L1 L2 of 1 plus HFE plus, now in this j and minus j gets cancelled and omega also. So remaining term is L1 and C. So L1 by C plus HIE. Now in these three terms j is common, so we're gonna take j as common. So j of omega L1 plus omega L2 minus 1 by omega c equals to 0. we got minus because plus into minus minus. Now this is the real term and this is the imaginary term. Now first we'll solve the imaginary term. So we got the imaginary term as HIE omega L1 plus omega L2 minus 1 by omega C equals to 0. So we're gonna send this HIE to the right hand side. So we'll get 0 by HIE. Anything by 0 we'll get as 0. So omega L1 plus omega L2 minus 1 by omega C equal to 0. Now we'll send this 1 by omega minus 1 by omega C to the right hand side, and we're gonna take this omega as common because omega is common in these both terms. So omega into L1 plus L2 close equals to, so here minus, when it comes to right hand side it becomes positive, so 1 by omega C. Now we'll send this L1 plus L2 to the right hand side and this omega to the left hand side. So omega into omega, omega square equals to 1 by C of L1 plus L2. Now we're going to consider L1 plus L2 equals to LE equation. So omega square equals to 1 by C of L equation. Now we're gonna send it square to the right hand side. So omega equals to 1 by under root C L equivalent. So therefore we know omega is equals to 2 pi f. So we're gonna substitute this in the omega place. 2 pi f equals to 1 by under root C L equivalent. So we're gonna send this 2 pi to the right hand side. We'll get f equals to 1 by 2 pi under root C L equivalent, which is this is the frequency of Hartley oscillator. Now we're gonna solve the imaginary part. We got imaginary part minus omega square L1 L2 of 1 plus HFE plus L1 C equals to 0. So now we're gonna send this L1 by C to the right hand side. So minus omega square L1 L2 of 1 plus HFE equals to minus L1 by C. So here minus cancel, N1 gets cancelled. So we know the omega square. We got the omega square as 1 by omega square. We got a 1 by C of L1 plus L2. So we're gonna substitute this omega square here. So 1 by C of L1 plus L2, remaining is L2 into L2 of 1 plus HFE equals to, so here L1 is cancelled, so 1 by C. Now in this C and C are common, so it gets cancelled. So we're gonna send this L1 and L2 on the right hand side and L2 also. So we'll get 1 plus HFE equals to L1 plus L2 by L2. Now we're gonna send this one also to the right hand side. We get HFE equals to L1 plus L2 by L2 minus 1. So HFE equals to L1 plus L2 minus L2 by L2. So in this plus L2 minus L2 gets cancelled, so remaining is HFE equals to L1 by L2. This is the beta value, which is the voltage feedback ratio.